The last session of the day. Now we're going to get into the industrial part of it, and it's a great pleasure to announce Neil Lawrence from Amazon, and he'll be talking about meta modeling and deploying machine learning software. So please.
Thank you, Anders. So I should say, although I'm on leave at Amazon, I'm also a professor at Sheffield, and things I say today are all my sort of academic opinion. They are not Amazon opinion in any way. So just bear that in mind. So what I wanted to start with, it was interesting to watch the adversarial learning. Well, first of all, it's a great pleasure to be on this stage because the first ever conference I attended was the Machine Learning and Generalization Summer School in 1997 that was held in this room. And I watched Jan LeCun and Jeff Hinton and David Mackay and Chris Williams presenting on Gaussian processes, or was it David Mackay? I can't remember. On this stage, Leo Breiman actually fell off the stage after insulting Bayesians and blamed it on the Bayesians. Radford Neal. I also met. Okay, so there has been a revolution, and I'm so pleased to have Pierce coming after me, who's just been doing amazing work with these models in the medical space, sort of things that are really going to change people's lives. And we shouldn't diminish what's going on. This one here is a Callista Flockhart detector that Facebook have produced. And it was the first face recognition system that got close to human performance. And one of the things I think the difficulties people have about it is understanding, okay, so this is about the maths of deep learning. And then people say, oh, these things are very mathematically complicated. Well, they're not from a mathematician's perspective. They're simple composition of functions. Right? So take some simple functions, compose them together. And they're putting in an invariance in the system, which in this case, for this design, they don't even model the invariance of her face. They actually took out that invariance geometrically first, and then they present the RGB channels and then compose functions. So it's not that complicated. And one of the interesting things to me is how interesting people found it that adversarial examples cause you a problem. Because anyone with any understanding of high-dimensional spaces and statistical models will know that straight off the bat. Because you're operating in your image space in such an enormously high-dimensional space, and we all know things about what those spaces look like. So it's absolutely no surprise that if you have knowledge of this model and what the gradients are of it, that you can find a point in that space which will give you some crazy answer. What's surprising to me is it's become such a meme. Now, I think it's still interesting because the theory that follows is also very interesting. But let's face it, it's not how we're going to get attacked adversarially in these systems in the real world. Okay, so here's my intuition for why, even for members of the public to think about why this can happen. And it's just to sort of say that deep learning is just like a pinball machine. So in deep learning, you're composing functions. Here, each row of pins is simply the parameters of the function. And here, we've just got one-dimensional inputs to one-dimensional outputs. So one-dimensional input, intermediate unidimensional variable, intermediate unidimensional variable. These are the parameters of the functions. And if I send a non-picture of Callista through the machine, because my parameters aren't changed, it falls into the yes bucket when it should have fallen into the no bucket. So this is the model at initialization. At each point, so we're entering the sort of function there, and then it's moving to there, and then it's moving to there, and then it's coming out. One-dimensional at each space, right? So it's not like the sort of deep learning people are using in practice, but you can get the intuition. Of course, when you train, what you get is a configuration of pins that gives you that mapping correctly. So now, after training with these 3 data points, the no Callista goes in the no one, the yes Callista goes in the yes one, the yes Callista goes in the yes one. That's not what the neural networks actually look like because they're playing pinballs in very large dimensional spaces. Now, even anyone with a sense of pinball, you have a sense of how many balls you have to drop through before you're going to hit all the pins in that system, where the pins are now the weights. Imagine that in a high-dimensional space where these pins are becoming sort of bars, because they're sort of like that. These ReLUs are sort of like bars in the space that are deflecting you in dimensions. As soon as you say, I'm going to start with a million-dimensional input, don't be surprised that you can find a place in that million-dimensional thing that will go through this machine in some previously unforeseen way, because you've never explored those parameters. You've never explored that route through the machine. Now, what I do like is the way that the work is shifting in that space to say, well, let's look at it, what happens, and some really interesting work we saw this morning, from let's look at what happens if we try and push a space around that data point through the machine, and how does that propagate, right? But to be fair, we understood that years ago, and the right answer for dealing that is to deal this probabilistically. So instead of having fixed pin positions and fixed input positions, you say, I'm just going to put this thing in, I'm going to have uncertainty over where these pins are, I'm going to have uncertainty of my path through the machine, and when I do that, effectively I look at a much larger part of the machine. So each data point, if I push it through the machine with uncertainty, I cover a much larger space on the machine. Interestingly, that is very akin to the solution people are proposing with adversarial machines. But even then, to think that you are going to solve all the problems of people manipulating neural networks with just that is wrong. Because in practice, the sort of adversarial examples you'll get is people putting stickers on their faces or stickers on signs, which are large correlated noises, which are only represented by a small area in this ball. If you want to capture them, then you have to have structured noise on your input and know what people are going to do. And you know, we spoke about that this morning, about how forlorn that is as an approach for dealing with adversaries in the real world. So let's get real and say, no, you're going to have adversaries. You're going to have 9-year-old kids messing with your system. And even when your system design was perfect, like so with Alexa, in effect, it threw an exception, I presume. I don't know. But I presume it's thrown an exception on the question, and then when it's thrown an exception because it doesn't have, it's not you at the time, this is a number of years ago. By the way, Siri does not do that anymore. Siri says it's an answer involving a lot of 9s or something now, because they wised up to it. I don't know what Alexa says now, they probably changed it. This is like 3 years ago. So it was hitting an exception, and the bug somehow prevented the error from happening. In the Siri case, it was performing perfectly, and that's what caused the error. And I find that fascinating because we're moving, if you believe anything that anyone is telling you about pushing artificial intelligence systems into the real world around us, the game that has changed is where we are choosing to automate. In the past, the way we automated processes is by building a controlled environment and automating within that controlled environment. So whether that's a factory or a motorway, driverless cars on motorways, I reckon it will work. Driverless cars in the city centre of Cambridge with tourists and cyclists and those weird wheel things people are using and all that, not so much. Because an uncontrolled environment throws at you all sorts of things that we just haven't even got the systems engineering to understand yet. And that's going to be the major blocker about deployment of real algorithmic decision making, which, as I think someone asked earlier, is going to involve, I think to the Center for Data and Ethics, there was a great question about that, is what happens when it's not just one model, when it's a series of interacting models. If it's just one model, and Pierce has a very nice use case which is effectively one model, that's great. But for every one model case, there's going to be some exponentially larger number of multi-models being combined together case. Okay, another thing that I like to point out is everyone gets excited about the changes that we think we are making by inventing AI when all we're doing is complex statistical modeling on the back of data. No one ever talks about those things. That is a container, and that is an automated port system. The influence of that is this. It doesn't create the cod, but this is wild Alaskan Pacific cod that was caught, is for sale in the northwest United States, so not too far from where it was caught, and for sale frozen. And this is the back of the packet. It's wild caught, and it's a product of China. How is that possible? Because after catching, it's exported to China for processing, and then it's exported from China back into the Northwest. Why is that so? That is not a crime against the climate in any shape or form, because the cost of that export is so cheap relative to the cost of processing that it's next to nothing, because it's being done in containers at scale. The cost of moving goods in our current economy is orders of magnitude cheaper than the cost of processing them. So when people worry about globalization and talk about it as an effect, they're talking about that. They're talking about containers. They're talking about the fact that we have an international system for moving stuff around extremely cheaply. And the major innovation, one of the major innovations that allowed it, because it basically got rid of manual labor at docks, is the container. I think Liverpool Dockers going on strike. I mean, it has revolutionized the way ports are. And I find it funny that we rarely talk about it, because it's affecting everything in your pockets. So my motto is solve supply chain and then solve everything else. Because it turns out the decisions you are making when you try and make supply chain more efficient, or you try and make your processing more efficient, are all the critical problems in machine learning that require a number of interacting models. Why is that? Because they involve things a lot more complex than just data-driven. Data-driven can help, but data-driven needs to go beyond that to understand economics and mechanism and how roads work and how ships work and all these sort of things that you don't just get from data. You have to have an understanding of how people are responding to different prices, different price incentives, or how they respond to different delivery rates, so on and so forth. And that's key, because what that means is that you need a mechanistic understanding of what you're doing. And the notion that I'm a machine learner through and through. I lived the data-driven world from 1997 when I was here all the way till today. But it's such ignorance to sort of ignore the world of operations research and decision making and the world of physical modeling and all these other things, because we can only interpolate in machine learning, right? We can only go between data. And we only do that by saying, oh, smoothness or translation invariance. However complex you think that deep neural network is, it's way, way simpler than the simplest of climate models that Peter works on. Yeah? So we need some way of integrating that understanding into our systems. And I think this is what the real world is going to look like of algorithmic decision making, that you've got the real world and then you have some set of simulators alongside the real world that are in some sense approximations to that real world at different levels of granularity. And the way you deal with that, you've got a problem, because this simulator says one thing, this simulator says another. This is one in climate modeling, that would be a simple, fast to run climate model. This would be a slower climate model. This is the real world. We only have one of them. That's why we can't do machine learning on it, right? You can't do machine learning on one data point. But what you can do is you can start doing machine learning to interrelate these things. So you can build statistical emulators, which are machine learning models of what the simulator would say. And they interpolate between different points on the simulator. And rather nicely, you can then calibrate back to the real world and use that simulator to try and introduce, that emulator to try and introduce information about the real world, how well calibrated your simulator is. Less so in climate, more so in systems like supply chain, where you have some understanding and some parameterization of that understanding, but you're also constantly watching how the real world goes and how it differs from what you're doing in your simulation. So this, I would call it emulation, because that's the sort of term that Tony O'Hagan, who's one of the sort of founders of this idea, used to use in Sheffield. It's also known as surrogate modeling. You can also think of it as meta-modeling, because it's modeling of a model. You've got a model that's a physical model, and you're modeling it with a data-driven model. So you can also have multi-fidelity emulation, where the machine learning model tries to learn what's in the one granularity of simulator and a finer granularity of simulator and the real world, and tries to learn the relationship between them. It is always doing this with uncertainty, because you want to be able to do things like, say, if I want to answer a question about this system, what should I do? Should I run this cheap simulator, this more expensive simulator? Should I try and acquire data in the real world? If this machine learning model has an understanding of uncertainty, if it understands what it doesn't know, you can begin to use this within a decision-making framework of what to do next. It can decide, well, I have confidence that this simulator, because I'm mapping it to this real-world thing, is performing well in this regime, and for the question you posed, I can take the probabilities, I can see that I can answer it just by running this simulator. Or it may say, I don't have the data in my emulator, I need to run a new simulation in order to answer that question. But you can try and optimize the simulation you run. And a simple variation of this is if what you're trying to do is minimize this, some sort of parameter in this space, that would be called Bayesian optimization. And there's a number of different things in surrogate modeling you can do. You can do integration, sensitivity analysis, answer all sorts of questions once you've got your emulator in place. Okay, and I think the other thing is you don't just have one emulator. So this is one challenge. You should design your emulator very often to answer a specific question or for a specific purpose. So what you need is the capability to deploy emulators as and when. Why is that true? Because these simulators are reasonably complex function objects, and your emulator is likely to be a simpler machine learning style function, particularly if it's going to be one that allows you to propagate probability through the function, then you're tending to be restricted in the classes of functions you can use. So you end up with a very interesting design challenge about what to tie your emulator to, how to do it in order to answer the question. So the interesting thing here is you want to be able to release these emulators fast. I mean, for climate, you can spend your time. We don't have that much time, but we've got a little bit more time than if you're using this to declare a delivery or work out a delivery or work out when which taxi should go to which individual. Okay, so this general field is known as uncertainty quantification. I haven't mentioned deep GPs yet because I've moved them down the thing. I'm not a fan of AI as a term. I think we should get real about using the right mathematical language to describe what we're doing. In the machine learning community, there's a great sub-community called probabilistic numerics, which is all about the uncertainty associated with computation. How close are you to the solution? Can you stop? Have you got enough information? They view computation, numerical analysis, as a decision problem. That you don't have the real answer because you've got some numerical approximation, but do you have a good enough answer? And in order to answer that question, you have to have uncertainty about what you're doing. Surrogate modeling is what I've been talking about, where your simulation is less directly interconnected with how you're uncertainty quantifying it. But each of these things gives you probability and allows you to do what we really want, because I think a much nicer term is just algorithmic decision making. But in order to make good algorithmic decisions, we know we need to deal with uncertainty, we need to understand our loss function, we need to represent these correctly mathematically. And people in OR have known this for years. The challenge has been that they haven't been able to leverage the large types of data and computation we have now. And that's the world that's become a reality. We can revisit those techniques in the light of this, economics as well. So you end up with trading off decisions. Should I compute or should I acquire data? And this doesn't just apply for supply chain. It would apply for an intelligent autonomous system walking around this room. Should it go to its simulation of the room? It applies to our own brains. Some of what we do, personally, okay, so I'll get all a bit Jeff Hinton on you now, because he actually did hierarchical community of experts on this stage for me, and he told me in 1997 that was how the brain worked. And the first time Jeff Hinton tells you how the brain works is the time you never forget. So I still genuinely believe that that's how the brain works, because he's told me it worked in several other ways. But actually, my Jeff Hinton moment is to say that what's really going on, and I'm just making this up, I'm not a cognitive scientist, your conscious mind is just a complex simulator of the world which works on a reduced abstract space. The real you is the emulator underneath that makes a call, please run this simulation so I can fit a Gaussian process in my lower animalian brain to understand how I should react to that world. It doesn't use a Gaussian process directly. But you see what I mean? What you think of as your conscious real world, what we know is not what's really in charge, it's something underneath. You can view that as a slow computing simulation, and the real you is the fast computing emulation that actually makes the decisions, because it's much better at assimilating a lot of information at one time. Okay, so how am I doing time-wise? So I'm pushing emulation as an example, and here's a sort of practical example that we have worked on when I was at Sheffield. So Formula One car, you want to design a Formula One car such that it performs well on track. But there are limits on how much wind tunnel testing they allowed you to do. There's like official rules on that. It's like 3 days a week. And there's limits on how much money you can spend on computational fluid dynamics. And there's definitely limits on track testing. You get to do very limited track testing. So you're looking to optimize your car design with these different models. One model is even a physical process, a wind tunnel. Another model is a CFD. There are different types of CFD. And you're looking to make an adjustment. And once you've made the adjustment, the question is, what should I do? Should I wind tunnel test this? Should I CFD test this? Should I take this out on the track? And with multi-fidelity emulation, we've shown you can do that. You can optimally go through making decisions in this type of decision stack. Very nice, because instead of having your instinct tell you, I want to run this CFD, you know in the region in which that CFD is performing and the region where it's not. So when you ask the question, let's say it's associated with a specific track, what's the right test to run, which I don't think they tend to do so much on specific tracks, but let's just pretend, is this CFD simulation enough to cover this track? yes or no. One very interesting thing I found out is that all of Formula One is about very slow speed corners followed by long straights, because if you carry fast speed through a slow speed corner before a long straight, you get that speed across the whole straight, and that affects your time more than anything else. The wind tunnels are not capable of recreating those conditions because they can't bend the wind across the car far enough. They bend it a little bit, but not at the slow speed corner. So the one most critical thing in Formula One in determining whether your car wins, these slow speed corners followed by long straights, you can't recreate in the physical simulation. You have to use CFD or something else to get that. So here's a sort of little example, mountain car simulation. I like this example because it was the reinforcement learning example of the day back in 1997. This is what we managed to do. So in that case, it's a physical system, and people do sort of learning algorithms. What you're trying to do is fit a controller for it. And it's actually relatively easy to fit a controller. This is a linear policy, which is effectively just a linear controller on the system. And what you can do is you can run searches. So if you do a random linear controller, it doesn't do anything. But already you can use surrogate modeling even in this space where there's an underlying physical model by just introducing Bayesian optimization. So what you do is you say, I'm going to try a particular set of parameters on the linear controller, and I'm going to sort of see what the performance is, and I'm going to fit that performance with my Gaussian process in this case, which is my emulation model. And I'm going to do that as many times, and I'm going to choose the next point in the way that gives me the most information about what the minima, or maxima if you're going for reward, but minima normally in optimization, what the minima about this function space is. And after only 50 iterations, this is just 50 operations of intelligent search in a relatively low dimensional input space, then you get a controller that does the sort of right thing. The key about this problem, by the way, is the car isn't powerful enough to drive up the hill on its own, so it has to learn to drive that way and build some energy. And then so it has to accelerate that way and that way. So it's a slightly more complex than what's obvious to a normal human. If your car was powerful enough, you would just drive up there, right? But it has to actually work out to do a couple of oscillations. So that makes it a little bit more complex than you might expect. So that's the sort of thing you do. That's just an emulation system straight out of the box, known as Bayesian optimization. But it ignored the dynamics of the underlying vehicle. It didn't know anything about that, what the system dynamics were. So the sort of thing you might do with an emulation is, first of all, emulate the dynamics. So in this case, the dynamics are trivial. They're actually much faster to run than the Gaussian process we fit to them. But in a complex case, the dynamics of how the thing's going to move next might be more complex, and it may be faster to just run the Gaussian process. So in this next example, we actually build an emulator of the dynamics, and what you see here is the reconstruction from the emulator. I'm just sort of showing you toy examples. The reconstruction of the emulator of how the car responds. And then instead of training on the simulation, which is very, very fast in this case, but could be extremely slow, we choose to train on the emulation. And in this case, we end up using only 500 calls to the simulator rather than the 37,500 calls to the simulation before. Why? We only had 50 iterations of Bayesian optimization, but each iteration required the simulator to simulate the dynamics multiple times, right? So here, what we do is we build the model of the dynamics, and then we operate on that instead. And I mean, you won't see any difference, but yeah. So this is the controller just using emulation instead. Now, of course, for this simple system, you can see that's not a big deal. But what you've got to imagine is a world where you can simultaneously deploy the emulator to decide what simulations to run. So you could be deploying the emulator in this case. When it's running the dynamics at any given point, it may even be saying, do I know the dynamics confidently enough now, or should I run the simulator again? And all of that's integrated. And it greatly speeds up your capability for making the decision, which in this case is building the controller. The final example we have is this multi-fidelity emulation. In the multi-fidelity case, we do the same thing, but we pretend we have a cheap, noisy simulator. I won't go through that again, but it's the idea there is you've got two simulators, one's good and one's bad. Now, if you want to play with this, we have some software that was built by an SDE intern we had from Dundee last year, who was very, very good, which give you a bit of a sense of emulation in an example, which is a simulation of taxi allocation. And if you search for MUKit playgrounds, you'll find it, and you can sort of just play around with these ideas. He built a visualization and a simulation of taxis, and the thing you can play with is optimizing the number of taxis on the road and emulating what it all looks like, just to get a sense. We built this for our managers so that they could try and understand what we're doing. And this is the sort of result, so you can't quite see the error bars here, but this is like trying to learn what number of taxis leads to maximum profit, and you've run the simulation three times, and you've got an estimation of where you are, and likelihood is you're going to run your next simulation probably in this space, because it looks like that space might have a better maximum, yeah? That's the notion, but you can do that if you want to get a sense of this live in MUKit Playground. Now, MUKit Playground is an instantiation of a tool that we built and released BSD license. This is the Amazon GitHub page for just doing emulation in general. And so there, we've got the playground there as one option, but MUKit itself is giving you a range of possibilities around emulation, decision-making frameworks, so Bayesian optimization, multi-fidelity emulation. Here it's showing a low-fidelity approximation and a high-fidelity approximation, fitting them together to make decision-making. You get things like experimental design, where should I move next? Bayesian quadrature, if you're trying to do integrations across a simulator, that requires a lot of simulations. It's a great use case for emulation. And sensitivity analysis, what's the sensitivity to any given input on that emulation? So that software is all available. That's coming out of my team. It's BSD license. We welcome contributors. We'd really like to make that the main repository for the sort of tools of emulation, so we can all just go to one place, and we don't want to be precious about it in any way. And a lot of these collaborators were interns with us and are back in their home labs and continuing to work on it together. Okay. Well, what's that all got to do with deep learning? Well, in the world of deep neural networks, okay, I've drawn it the other way up this time with the inputs on the bottom and the output on the top. This is the type of model we might want to use for emulation, but what I said before is that these models aren't that great. Now, I've introduced bottleneck layers in here for a reason that will become clear in a moment, but a typical fully connected neural network would just have these lines going from one layer to another. Now, what we do, and what we have done for a number of years, and there's a nice paper about doing this in Bayesian neural networks, but our attitude has always been you need the uncertainty in these systems. And the way we do that, you can think of it as the following. This is a neural network where we've introduced so-called bottleneck layers, which are just linear layers. So you could think of it as doing an SVD on the weight matrix on each layer. I think when I first talked about this, no one had done this, and since then people have done it, and it's a paper, and everyone gets excited and whatever. But it's just sort of obvious that you can reduce parameterizations by SVD, right? And then you can call these additional neurons or bottlenecks or whatever. But actually what you've really done here is you've built a basis function model. Now what you can see is you're doing a very natural composition of functions. At each layer you've now got inputs to a set of basis functions, which is going out to a new set of outputs. So this is a multivariate linear model with basis functions. Now, if you now do the following, if you now say I'm going to extend the number of basis functions in each layer to a large number of values, what you get, so it's a cascade of neural networks, of single layer neural networks, you can think of that. But if you say, I'm going to ignore the fact that these are basis functions, and I'm just going to sort of say that I've just got functions there, you can now declare these functions, each of them, with intermediates to be Gaussian processes. And what you have is just straightforward composition of Gaussian processes. Okay? And that is nice because Gaussian processes handle probability well. It's got disadvantages because they handle probability well in each layer, but as you push the probability through the next layer, you get sort of non-linear things happening to your probability. It becomes intractable. So you end up looking for approximations, and that's what a lot of work in this space is. But this is just simple function composition. And the really nice thing about it is if you look at this chain, and we don't always do this, but if you look at it in this form, if you put the number of units in each hidden layer to be the same, you've just got a Markov chain. So there's nice work by Mark Dunlop, Mark Girolami, and Andrew Stewart analyzing the properties of these things as a Markov chain. So you can say, how deep can I make this if I make each of these layers the same? You can start doing some really nice mathematical analytics, because instead of this very ugly neural network function, which is, the problem with these is they're hard to fit on very large data sets. That's a really interesting thing, what's going on in neural networks. After 1997, we all moved to Gaussian processes. I watched Jan LeCun present LeNet 5 on this stage. It was amazing. And then we all started doing GPs and kernel methods and graphical models. Why? Because they're mathematically far more elegant, but they're algorithmically way more complex, and they turn out to be hard to scale. So neural networks came back because we got so much data, and the algorithms were so simple, we could scale them very quickly on GPUs, and we could fit them to very large data sets. But I don't think you should believe in any shape or form that means they're the right model. They've got many, many bad characteristics. And if we can get the algorithms right for these other models, then we can quickly move on to the next neural network winter. Okay, so here's a little data set to illustrate this. I like this data set because it's marathon data, and I do a summer school in Uganda and Kenya, and they like marathon runners there. And there's nothing better than winding up the Kenyans by talking about Stephen Kiprotich, who's a Ugandan who trains in Kenya. He won the London Marathon, but the Kenyans now the fastest, so they're not upset anymore. Anyway, this is a dumb data set, but it's one-dimensional, and it's got some interesting characteristics that in 1904 they actually got lost. And I can't run a marathon that fast, but I could have it as a realistic ambition. But I wouldn't be able to if I had to chase cars choking up dust and I got lost. So it's got an outlier. So it's got some interesting characteristics of noise. Alan Turing, by the way, I keep saying this, and now you can see it appearing more publicly, but I sort of dug this out, found out this one day. He ran a marathon once in 2 hours, 46 minutes. That was I think it's the 8th fastest marathon in the London Championships, and that year the marathon was won in 2 hours 30. It's 1946, and he won it in 2 hours 46. So he probably wouldn't have won the 48 Olympics, but it's not impossible. So you can ask that question, and that's an interpolation question. If you just fit a regular Gaussian process to this data, you get classic things that you would expect to happen, because you've got homoscedastic noise. So the noise is the same everywhere, so you get some sort of averaging of the noise level, and it doesn't sort of understand that things can change. If you do a deep GP, and this is exactly the pinball thing, but only 2 layers of rows, because it's one-dimensional input on this deep GP, one-dimensional output going into a one-dimensional input GP going to one-dimensional output. You can change all those parameters. You're free to. Do what you like. But in this case, it's nice because I can show a result visually. So this is the fit. So what it realizes is that there's heteroscedasticity in the noise. The noise is starting large and going small. This is something, by the way, you don't need, for the mean function here, you don't need the deep GP. To capture the uncertainty and the crazy nature of the uncertainty, you do. Even though these are very, very powerful functions because they're infinite width basis functions, so people will get excited, oh, these are samples dropping through the deep GP, because what I'm showing you here is the approximation to the output variance, because it's not Gaussian, it's non-Gaussian. So these are samples showing that actually it does look like it's roughly Gaussian in this case. And the reason it does look roughly Gaussian in this case is this is what the model does, something very, very simple. It takes the year, it puts it into that latent variable, that intermediate layer between pins, and it does so with a certain amount of noise. And then notice this flattening. This flattening is sort of important. So this is by 2000, that's flattening off, but it's moving quickly before then. Then it pushes that through this function that looks very close to the function we're seeing, but has much less noise. But notice what's happening. That flattening there is mapping all this data into the same place. It's all coming out at 4. So at the next layer, you're seeing all the data coming in from 4, which is the most recent data is all coming to the same point. So that's what's giving you this effect where it flattens out. So it can do that with 2 nonlinear functions, relatively easy, not very complex nonlinear functions. But the uncertainty is important because although the uncertainty on the inputs of this is the same, it actually is sort of saying, well, what really happens is there was some sort of uncertainty on the inputs, and because the gradient here is large, that's led to a large uncertainty on the outputs. Whereas the gradient here being flat leads to a small uncertainty on the outputs. It's quite nice. Now, this is the pinball plot. This is my new. If this plot isn't useful, don't tell me, because it took me ages to code this up in matplotlib. So in my mind, I've lost track of whether it's interesting, useful, or not, and I don't care. I'm going to show it to you anyway. So this is the points coming in, and you can think of them falling through the machine as a sort of with sort of Brownian motion, right? So so that they get some variance on the way out, which the standard deviation is increasing with the square root of the fall. And then at the next layer they do the same, right? So here it's all Gaussian, but the next layer they go through a nonlinearity. So I'm showing you resetting the variance as it goes through, but in reality the variance propagates. So what you're seeing is all the sort of data from 1970s onward projects to 2010. So that's the sort of nature. That's also available publicly in software if you want to use it. And we call that MX Fusion, which is our probabilistic programming language targeted towards that. And that's pretty much all I wanted to say, that there's some really cool statistical models which have much more interesting mathematical properties. They're going to be vital in deploying much more complex systems. Thanks very much.